lesson is on inverse trigonometric functions. This is section 4.6 from your book. So in the past we've learned about inverse functions, just general inverse functions. We have some f of x and we try to find f inverse of that function. And so if we recall that inverse functions, the way we did that, we had a swap of x and y. So if we had y equals 2x or something like that, the way we found the inverse was by swapping. So we said x equals 2y, and then we solved for y. So we would get y equals x over 2. That would be our inverse function. So we did a swap of x and y. And then that inverse function would cause a reflection about the line y equals x. So if you can imagine y equals 2x, that has a slope of 2, it's linear. Y equals x over 2 has a slope of 1/2. So if you imagine that y equals x line is in between those two, it's a reflection. This was your y equals 2x, for example, and maybe this was your y equals 1/2 x. So they had a reflection of each other around that line y equals x. So given a function f of x with some domain a and some range b, the inverse function f inverse of x will have the domain b and the range a. So they swap. We remember that whatever our domain was and our range was is going to swap for our inverse function. So given that, the inverse of sine of x, when we talk about the inverse of sine of x, we have sine inverse of x. And we remember that this is not the same as the reciprocal, right? The reciprocal of sine is actually cosecant. The reciprocal of sine is cosecant. The inverse of sine means a different thing. It means we take the sine of something and we actually end up with our degrees or our radians. So the inverse of sine of x, sine inverse of x, is also called arc sine. So a lot of times you'll see it written as sine to the -1 of x, or you'll see it as arc sine or arc sine of x. That's another way. So similarly, the inverse of cosine we know is cosine to the -1 of x, cosine inverse of x, inverse cosine. We also call this arc cosine or just arc cos of x. So now that we have the terminology, let's talk about this. So in order for the inverse to be a function, the original function must pass the horizontal line test. You guys remember this from chapter 1 where we said a standard function is a function if it passes the vertical line test. That function's inverse will also be a function if it passes the horizontal line test. So we take our pencil, we say, do we have more than one value? And if we look at this sine function, well, it doesn't pass the horizontal line test everywhere. But if we restrict it from -pi/2 to pi/2, then we actually do pass that horizontal line test, which means that our inverse would be a function, which means our inverse would pass the vertical line test, as you can see. And when we have that reflection about y equals x, we get the function that looks like this. So we know what our sine function looks like. We go through 0, we have a curve up with a max at pi/2. So our inverse sine function from 0 to, remember that our y and our x are going to switch. So now our x goes from 0 to 1 because our y went from 0 to 1. And now our y goes from 0 to pi/2 because before our x went from 0 to pi/2. So basically you're just shifting this whole graph because you're making a reflection of it. And if we wanted to talk about the domain and range of this, now we notice that the domain of y equals sine inverse of x is from -1 to 1 because that was what our range was for the other function, for our standard sine function. And our range for this is from -pi/2 to 2. So cosine works the same way. The place we're going to run that from is from 0 to pi. And that will give us our function. So our range on inverse cosine is from 0 to pi, just because that was our domain for the restricted cosine function, and our domain for our inverse cosine is from -1 to 1. This is true all the time unless you have like cosine of 2x and you're taking the inverse of that. But our inverse cosine, you'll notice, it has dots right here, right? It means that it does not continue. Usually we're used to seeing on graphs of a function that we have some line that extends up and goes on. That's not true here. We don't continue going. Our graph stops at -1 and it only goes up to 1 for our domain. So So let's do an example using inverse sine. So this question says find the exact values of each expression if it exists. So the question says find the sine inverse of 1/2. So what does that question mean? That question means where do we have some degree where we get the answer 1/2 if we were to take the sine. So where are we looking for sine? We're looking at our y's, right? We're looking at our y coordinates. We want to find which degrees we're plugging in, which radians, which angle we're plugging in, and we get a y value, our y coordinate, equal to 1/2. So if we look around here, we notice that, well, at pi/6, here is where we have that 1/2. Similarly, we're restricting that domain, if you remember. So for our restricted domain, we went from -1 to +1 for our sine. So we also have this 1/2 over here, and that would give us 2 of the same values per question, which is what we're trying to avoid, which is why our sine is just this half. So we only care about over here, and we get that 1/2 at pi/6. Let's look at arc sine, which is the same thing as sine inverse, of -√2/2. So again, we're looking over here. Where do we have a -√2/2? Well, we have it right here, which happens at 7 pi/4. You could also call this -pi/4. That's an easier way to refer to that, because we didn't actually go all the way around if we're only considering 1/2 of this sine curve, right? We didn't go all the way around to 7 pi/4. We just went from -pi/2 to +pi/2. So really that 7 pi/4 is called -pi/4. Let's look at the last one, which says sine inverse of 3. So what value do we get 3 as our y coordinate on this unit circle? Nowhere. Nowhere do we have a value that is equal to 3. If it said 1 or -1, well, we might have a value that we can play with. But 3 is bigger than any value we have on here. So let's move on to cosines. This is going to work the same way, where it says cosine of -1 equals -√2/2. So now for cosine, we are considering just this half. These will give us all unique values for that cosines. We're going to have our positive x's and our negative x's. And that'll be the easiest way to get that, so that's where our restricted cosine is. So we're looking for -√2/2 for our x. Where do we get a -√2/2 for our x? Happens right here at this 3 pi/4. So that would be your answer. Your answer would be the 3 pi/4. Okay, restricted tangent functions. We also want to do this same in order to figure out what the inverse of tangent is. Again, the same way we had inverse of cosine, inverse of sine equal to arc cosine, arc sine. We also have arc tan, which is equal to tangent inverse or inverse tan. That's equal to that, arc tan. So for our restricted tangent function, we are going to restrict that from, as you can see, -pi/2 to pi/2. That's going to give us a 1-to-1. We're going to pass our vertical and our horizontal line test in order to get that inverse tangent function. Our inverse tangent function is going to be a tangent function from that -pi/2 to pi/2 that is reflected around that y equals x. So if we look at y equals x, maybe it looks something like this. We have a graph that's reflected around that. So instead of going curvy up here, it goes curvy down. Instead of going curvy down, it goes curvy up. And obviously our values switch, right? Our y's become our x's become our y's. So our domain is from -1 to 1 because that was our range before, and our range is now from -pi/2 to pi/2 because that was our domain before. So let's look at an example of this. Find tangent inverse of √3. So where we want to find a point, an xy on that unit circle, where we have y over x, right? That's what tangent equals to, and we get a √3. So if we look up here, we have at pi/3, if we were to do square root of 3/2 over 1/2, that would look like this. We would have square root of 3/2 over, if we want to divide by something, we multiply by the inverse of it, so 2/1, which gives us square root of 3/1 at pi/3. So that is going to be your arctangent of square root of 3. Now let's move on to composition of trig functions. So we know compositions of functions before. We take some f of some other function. So we can do this especially with things like sine and inverse sine. So the answer to an inverse sine question, whatever your answer is going to be some angle, some degrees or some radians. Well, we know we can take a sine of some radians or some degrees. So that is how sine of inverse sine of some number works. So in this example, we have sine inverse of -1/4, and we're taking the sine of that. The inverse property would apply. We would cancel out those signs and we would get -1/4. The important thing on here is that you have to have a restricted domain of each of the functions. It has to apply within that area. So this question says find the exact value of cosine of tangent inverse of -3/4. So let's look at the tangent inverse of -3/4 first. We're going to let that equal u. So we have cosine of some u. That's really what we're doing. And that u is equal to whatever the tangent inverse of 3/4 is. So that means u is equal to -3/4. I'm sorry. That means that the cosine of u, if we get this triangle out of that, that we have adjacent over hypotenuse, which would be equal to 4/5. We got our 3, 4, 5 triangle going here, right? If we have 3/4 as our tangent, we have our opposite over our adjacent. That means our hypotenuse, if we do Pythagorean, we're going to get 5 over here, and our cosine of that is going to be equal to that 4/5. So let's work this out again. We're saying that tangent inverse, some tangent inverse of some angle u, we get some answer. U is equal to the tangent inverse of -3/4. Or we could say this differently. Tangent of u is equal to -3/4, right? And that's equal to opposite over adjacent. Right? We can write tan u, we can switch them because u is equal to tan inverse. We're allowed to switch our x and our y. That's all we're doing here. Well, we want to take the cosine of u. Well, we know that u is equal to tan inverse.